Okay, so body of mass 6 kilograms is projected along a horizontal track with an initial velocity of 28. While it's moving, the body experiences a resistant force of 0.12 plus 0.06 v, where v is the speed of the body. Find the time taken for the body to come to rest. Okay, so to start with, we'll do a little force diagram. So there's our body there, and it's moving horizontally. Okay, so I've got the direction of motion there, showing it moving to the right. Now when you look here, the only force that we've got is this resisting force. Okay, there's no other force there. There's no forward force. There's no attractive force. Okay, there's no driving force. We've just got a resisting force. So we'll put that in. So if there's no driving force, well, of course, this body is just going to end up coming to a stop. Yeah, and that's the question here. So let's find the time for the body to come to rest. So essentially it's slowing down. Now of course something did give it its motion at the start, and it does say, yeah, it's with an initial velocity of 28. It's projected. So in other words, it's given a push. So when t is 0, okay, so initially, yeah, we see that it's got a velocity of 28. So it's given a bit of a push, and then it sort of slows down, okay, due to this resistance here, okay. Well, what we can do now, okay, is because there's motion, we can apply Newton's second law of motion in the direction of increasing motion. Okay, now of course we know Newton's second law is the resultant force equals to mass times acceleration. Alright, now the resultant force will be, when we look at this now, the forward force is, well, there's nothing, yeah, there's no driving force, that's 0. Take away then the resistant force, which is sort of all of this. So we need to package that up and put it in a bracket to show that we're taking it away, and equals to then the mass, which is 6, and the acceleration then a. Now we can turn this into a differential equation, and in this case we're going to connect v and t, velocity and time, okay, because they want us to work out the time taken, so we need to have t in there somehow. We know about v, we've got v involved here, so we can say, look, since a, we can replace a with dvdt, yeah, okay, because remember, acceleration is how velocity changes. Okay, the rate of change of velocity with respect to time. So we can replace it with that, and we've got something relating v and t. So here this just becomes minus 0.12 plus 0.06 v equals to 6 dv dt. What I'm going to do then is I'm going to separate the variables. So I've got myself a differential equation. I just need to separate the variables. So I need to get the v's on one side, t's on the other. So this needs to go over here. Keep the, you need to get the dv and dt on top. So the dv is already on top. This dt, because you're dividing, you need to take that over to get it on top. Take it over there. Now it could be slightly smart, because I could take that dt over here. So in effect I'm swapping it with this. But I can keep the minus there. Okay, that would probably be wise to do that. Keep the minus there. And then on the other side, I've just got 6 there, and keep the 6 there over 0.12 plus 0.06 v dv. Okay. And then a couple of things you could do. You could put that minus outside the integral because it's a constant. And you could put that 6 outside the integral because it's a constant. And then you need to ask yourself, okay, well, how do I... Oh, what am I doing here? How do I integrate this? Okay, how do I integrate this? Well, this side's easy because you've got a minus, yeah, but it's just 1 dt. So when you integrate 1, you get t, so that'll be minus t. This side's quite easy as well. If you look on the bottom here, okay, it's a linear term, isn't it? And of course we know we can use ln when we integrate, or more specifically, we've got that rule of me that if you've got the bottom as f of x, and then the top is the derivative of it, f dash of x, then the result becomes ln f of x plus your constant, so ln of the bottom. Now when I differentiate the bottom here, I get 0.06. Now on the top I haven't got 0.06, I've got 1. So what I can do, as we did before, I can change that to 0.06. Okay, I can times it by 0.06. So I'm timesing the top by 0.06, but to pay back then I've got to divide by 0.06 there. Okay, right, so it sort of cancels everything out. So this becomes 6 over 0.06 ln then of the bottom. Okay, now because v is the speed, I don't need to put modulus brackets here. Okay, I don't need to put straight brackets because v is the speed, it's going to be positive, so I know this is positive, so I don't need to worry there. That of course then becomes plus c. Okay, so that becomes minus t equals to, that actually becomes 100 ln 0.12 plus 0.06 v plus c. Okay, so I know when t is 0, v is 28. So plug that in. So I've got 0 equals to 100 ln 0.12 plus 0.06 times 28 plus c. So when you do all that, that means c comes out to be minus 100. Okay, ln 1.8. Okay, so we've got c to be that. Plug it in there then. So minus t equals to 100 ln 0.12 plus 0.06 v minus 100 ln 1.8. What we can do then is put this together. Okay, all right, or in fact what I'm going to do, I'm going to times through by minus 1 first. So I have 100 ln 1.8 minus ln minus 100 ln 0.12 plus 0.06 v. Okay, so that means then t will equal to 100 of this, take away 100 of that, so we can write that as a single logarithm. Okay, and then of course when it comes to rest, v is equal to 0. So when at rest, v is equal to 0. So when I put 0 in there, t comes out to be 270.8 seconds.